Hi everyone. It has been slightly over a week since National Day, and so I think it's a good time for us to look at some of the problems which I had proposed. And if you have not yet tried them, the link is still in the description below. Feel free to give them a try before watching the rest of the solutions. Now, I'll talk a bit about how each of these problems came about, but just to summarize, in case you didn't see the previous video, I came out with 8 problems, and each of these problems, the theme is based on an anagram of Singapore, which the first problem, the anagram is pie oranges. Obviously, it has to involve the words that I mentioned there, as well as possibly the theme that I've mentioned there, but not literally pie oranges, because it would be pretty hard to go to the supermarket and buy 3.1415 oranges. So the question here has an orange with radius 2 cm, and the question is asking you what's the minimum number of points which must be drawn on its surface such that there must exist 2 points for which the distance between them is strictly less than pi centimeters. The first thing is that we can try to understand what would be the visual implication of pi centimeters. How does it look like? And if we were to just draw a circle, the circle that passes through the center of the sphere. So if you cut it in half, you slice the orange in half, this would be 2 cm. The circumference would be equal to 2 pi r, which is 4 pi. And so pi centimeters would be this quarter circle. With that in mind, we can ask ourselves, what would be the most that I can squeeze in without less than pi centimeters between any 2 points? I believe this is fairly intuitive actually. If we were to just draw a sphere, which I am not very good at drawing, but let me try. If we draw a sphere, it would make sense to have the points at the top and bottom, and then just pick 4 points along the sphere which are evenly spaced. So this would basically just involve 2 circles, and each of the circles you just pick 4 points on them. So this would give you 6 points. The distance is all going to be pi mostly. Obviously, we are not talking about the ones that are opposite each other, but the ones that are next to each other have exactly distance pi. And so intuitively, we would expect that the answer is 7. Which indeed it is. And if we were to treat this as a short answer question, you can quite safely move on with the answer being 7. If you'd like to prove this a little bit more carefully, let me give a quick sketch of how you would do it. Firstly, just by rotation, let's say that the first point we pick is at the top. Now, straight away, if we were to put the one at the top, the entire top hemisphere cannot be used if you are trying to make the distances all at least pi centimeters. So essentially the question now becomes, in one hemisphere, how many points can you put? Now, if you did put a point at the bottom, then obviously the only place you're allowed to use after that will be the circle at the equator, and that will only give you at most 4 points, which is the thing that we did just now. So let's say that we do not actually use the point at the bottom. Then the idea is very simple. In each of these 1/8 spheres, which is roughly demarcated by something like this, each of these 1/8 spheres, you can at most put 1 point in each of them, with the exception of the 2 extreme endpoints like this. So with that exception, otherwise you can put at most 2 points. And that's because between any 2 points, if you were to just draw a line between them, it's going to occupy less than 1/4 of a big 2 cm circle. So basically 2 cases. If we use the north and south pole, and if we only use the north pole, both of them give you at most 6 points if we want to maintain the distance of at least pi centimeters. And so therefore, this will tell you that 7 is indeed correct. I'm omitting details here because this is still meant to largely be in the style of round 1 problems. So I just give a rough explanation. Second problem is this pairs gone, and I thought of just a game like the good old-fashioned memory games where we just find a pair and remove it, but there wouldn't really be much to count in such a scenario. So instead, what I've given you is the numbers 1 to 9999 written in a row, and whenever there's a pair of numbers with exactly the same combination of digits, Faisal can remove them. He does this until there is no longer any such pair. How many pairs will be gone at the end of the game? So how many pairs will be removed? Now take note that I asked not how many pairs will be gone at most or at least, because as long as we just keep on removing them, your numbers essentially come in groups. So for instance, 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3, and blah blah, all of this here would kind of be its own group, and you just remove 2 of the same group until there is either 1 left or 0 left. It doesn't matter what order you do it in. And in this case, there will be none left because there are 24. There are 4 factorial of that type. So this is the logic. And I think what we can do is to just split it by the number of digits, because the small digit cases are very trivial. So I just look at what will be left at the end of the game, and that will allow me to see how many pairs I got. Now for 1 digit, everything will be left, right? 1 to 9 will only be standalone numbers, so nothing can be removed. Now I have a footnote here. The footnote says that the digit frequency also matters, so 2023 and 2003 are not considered to have the same combination. It is the same frequency as well. So that's for 1 digit. For 2 digit, all of your reversers can be removed. So what will be left will be just your 11 to 99. Obviously those are standalone, as well as the ones with zeros. 10 to 90 will also remain. Those are the only ones that will remain, because those are the only ones which you cannot find the reverse to pair up with. Now, 3 digit is interesting because, again, the reverses are going to be all taken up. So let's say you have got 1, 2, 3 versus 3, 2, 1. You have got, let's say, 5, 5, 3 and 3, 5, 5. These will all be removed. So which ones will actually stay? First of all, 111 to 999 will all stay again. Right? Those are definitely going to not have any counterpart. In addition, all of the palindromes are going to stay. And at this juncture, we say all of the palindromes, but there is a slight bit of nitpicking to do. So this is a bit sneaky. Now we know that I want to talk about this combination of ABA, but the 111 to 999 has already absorbed the A equals to BK. So technically I can remove that and just put it as palindromes ABA. But we can also just think very carefully. If A equals to B, that's okay. A not equals to B, that's also okay. That's not the issue. The issue is the zeros in that. Now you realize that based on what we have written earlier, all those that end in a zero cannot be reversed. So those ending in a zero, we have to check what happens with them. If we have got, let's say, something like 120, then it is okay. Because for something like 120, 210 would also be that. Just reversing the front part would cancel it off. But for something like 110, it would actually pair up with 101. Because 110 would be left over, 101 would also be left over. And so all the scenarios where B is actually 0 would be removed. So all of these things are going to be left behind, which would be when A and B are just from 1 to 9. So this would leave you with 81. That are left over. But something is not right with this. Can you see the problem? The way that we can detect the problem is that if this is all, then the 3-digit numbers, there are 900 of them, and we have removed 81, that means that there are odd number remaining. Now an odd number cannot possibly have been paired up. And so this is a way that we can detect that, oops, I've forgotten something. And surely what I've forgotten is going to be something that is not in this category. It's not those that are ending in 10 because I have already described how those will be paired up. It's those ending in 2 zeros. So 100 to 900 or just A00 where A is from 1 to 9. So this gives you another 9 more that will be left over. So you see that this is a little bit tricky, it is a little bit confusing. And if we want to handle the 4-digit case, it's possible that we don't want to do something like this. So what I'm going to do for the 4-digit case is probably the one that's a little bit more generalizable, because at first we thought that we could maintain this 9s and 81s, but this is quite confusing. I'm just going to say that for any combination, it will appear an even number of times with just a few exceptions for 4-digit. Now, if we have got A, B, C, D with no repetition, that will give you 24. That is even. If we have one pair of repetition, that would be 12 combinations. If we have two pairs, that would be 6 ways. And if there is a triple, that would be 4 ways. So all of these are all even, which means that the first thing that I will write down are just the A. Obviously, those are going to remain. Now, what's left are the combinations that involve a 0. If it involves a 0, then not all the arrangements will work. So again, we will just need to check on those possibilities. If we have got 1, 0, it is going to be these cases. If we have got 2 zeros, there are these cases. And if there are 3 zeros, there are these cases. Now, if we did a quick count, some of them are okay, some of them are so-called not okay in terms of the number of arrangements that are going to be possible. Are they even or odd? So this one's even and this one's even, but for the rest of these, they are going to give you an odd number of arrangements. And an odd number of arrangements just means that there will be one left over. So we need to count all of these. Which is why this question is a very, very mistake-prone kind of a question that is more likely to be in the SMO Open than the SMO Senior, I would say. Okay, so how many of this AAB0 are there? Now I can write this like that because we are basically going to be just left with one representative permutation, right? So I'm just going to literally say AAB0 is the one that I choose to designate as left over. Of course, you may designate a different combination of a different permutation of this to be left over. Now, so this one would just give you 9 times 8 choices, and the rest of them are going to give you 9 choices. In other words, we can just count directly how many are left over. We've got 9, 18, 90, and 108. So that's how many are left over. And your answer is 9999 minus 9, 18, 90, and 108. So this would be the number of pairs that are removed, 4,887. Now, to be honest, for a question like this, I don't normally work out the answer beforehand when setting the question. I just know that it can be done. And the same for question 3. There's a little bit of a double meaning here because, PIE groans. PIE, of course, in plain English is pi. It is our expressway, but in Math Olympiads, it is the principle of inclusion and exclusion, which I have written as another footnote. The principle of inclusion and exclusion, and usually we don't like it very much. So groaning about PIE solutions is a very common thing. Here, I've literally asked you to arrange the letters in the word groans. And also, if you notice, tongue-in-cheek here, this is also the word sarong, which is thematic for our National Day. We want to arrange it such that there's exactly one of the sequences in the arrangement. And this is a classic PIE, right? So if let's say that you want to count arrangements where SA appears inside, it means that you treat this as one block, and now there are just 5 things to arrange. And the same for if you insist on RO or NG. All of these are 5 factorial. Now, if you want to have 2 of them inside, any combination of 2 of them means that you have just got 2 pairs and 2 single letters left over. So 2 pairs and 2 single letters are 4 objects. There would be 4 factorial ways to arrange them. And if you insist on all 3 of them, then there are just 3 pairs to arrange, which is 3 factorial. So this is not the big problem. The big problem is in how are we going to put these things together? Because the question asked for exactly one of these sequences. You can't use classic PIE, which means add, subtract, and add. That would be giving you at least one, not exactly one. So what I like to use is that if it's 3 things, we can use a Venn diagram, but in a very conscientious way. Which is that my target is I would like to have this region, and this region at the end. Now, first of all, I'm going to add all of this. So 5 factorial, 3 copies of it. Now, when I include the ones that have SA inside, it means that I've gotten this. The ones with RO means I've gotten this. And with NG means that I've gotten this. And so I have got a lot more than what I wanted. And so I need to subtract off this second column. But I don't just want to subtract it off to make it count once. I want to make it count 0 times. This here should be gone. Which means that I need to, let's say for SA and RO, that will be here. I need to subtract it off twice. So I need to subtract the 4 factorial, 4 factorial, 4 factorial 2 times each, which is going to do something a bit weird. Oops. Not that. What it's going to do is that you subtract off 2 dots here, 2 here and 2 here. The middle is going to have a deficit of 3. So you have currently minused it off 3 times. And so we need to add it back. And so this 3 factorial here needs to be added 3 times in order to count it 0 times. So if we count this, 3 times of 5 factorial is 360. 6 times of 4 factorial is 144. And 3 times 6 is 18. There are 234 ways that this can be done. Question 4. Now this is not something you would expect in an SMO of any type, but there is a bit of an algorithmic flavor to this. I believe that for those of you who are interested in taking Math Olympiads, there is maybe a slightly higher percentage than usual of you who are not very fond of your NAFA tests. And so this is just a bit tongue-in-cheek that we want to minimize the amount of pain, and obviously in terms of preparation and effort, some of the stations for your NAFA test are going to require more effort than others. Arguably pull-ups and your 2.4K run will require more pain, although that's very debatable. It really depends on your personal physical abilities, so this is just very fictitious. Now, I did think about getting a gold for NAFA test a little bit when I was a student, and thinking about how would we be able to strategize to just get a gold, right? Obviously you don't do that, but hypothetically. And the rules are that you must have at least 3 points at each station, which is a grade C, and a total of 21 points. Now this is basically meaning that in addition to the bare minimum, you need 3 more. And so what we will do is we start off with all of these, and I want to just take 3 steps upwards, and I would like those upward steps to be as small as possible in order to minimize the total. So you just compare them, and it is pretty obvious that we don't have to worry about the last two, because the difference here is going to be way too much. We definitely don't want to go for these because the rest of them are very small. This is just +1 and this is just +1. So really the difficulty here is just to compare the increase in all of these few things. The good news is that these are actually pretty far apart, mostly, so that if we just do an initial rough 1 decimal place estimation, that already can do the trick for most of these, right? So if let's say that we just to 1 decimal place 1.7, 2.2, and for these ones a little bit less well known, but you can do a quick estimate to just check. This is about 1.4, this is about 1.6, and this is about 1.7. Now it is not too surprising that the jumps between cube roots is going to be less than the jumps between square roots, right? This is very, very intuitive. Now the jumps between logarithms is probably where it is a little bit more tricky. We aren't used to calculating most of those, except for the fact that we know this is 2. So the main question is, how far apart are these logarithms? And so if I were to just look at this gap here, which is log base 2 of 4/3, how much is this compared to the roughly 0.2 or 0.3 margins of your square root and cube root? And the answer is actually quite a lot. This is not that small. Now, this is not that small because this is 1 over log base 4/3 of 2. You know, that does not look like a very smart thing to do, but then we can say that 4/3 squared is less than 2. 4/3 cubed is more than 2. Meaning that this here is between 2 and 3. Between 1/3 and 1/2. Now if it's between 1/3 and 1/2, that means that it is quite a big value already. So I'm not very interested in making this jump here. And likewise, if we look at the other one from 4 to 5, it is still not something that we are terribly interested in. And so therefore, the best thing you could do is to jump using your broad jump. To here, that would only cost you about 0.3. And then after that, because this gap from root 3 to root 4 is still less than the gap from log 2 3 to log 2 4, you would like to just jump up here. So it's a sort of a greedy based solution. This is not actually always true, because if let's say that you have suddenly got something that is a very small gap later, you might want to sacrifice on the first step to make a huge jump followed by a very tiny jump. But in this case, we don't have to worry about that, because these are all functions which kind of behave well. So no weird jumps. the gap between log 24 and log 25 would correspondingly be also a bigger gap than the cube root and the square root. So 3, 5 for 3, 3, 3 would be the levels that should be targeted. Question 5. I think we are all very familiar with the fact that for many of the National Day publicities, materials, advertisements, the National Day parade itself, we very often have Chinese, Malay, and Indian, and Eurasian or other ethnicity people, students, or items, or clothing, or languages all represented. This is a very traditional Singaporean style of celebrating National Day. And for this problem here, unfortunately, I couldn't really make it 2, 2, 2, 2 for the purpose of the counting being nice. Now, there's also a lot of effort in the position of standing. I'm not sure if you've noticed this, but there's always some effort in trying to make sure that people stand in an appropriate way. And so here, no two students of the same race are allowed to stand next to each other or directly opposite each other. Now, there is no reason why they cannot stand directly opposite each other, except that I'm trying to make the question work. So apologies if that sounds very strange. Now, in how many ways can this be done? And note that rotations and reflections are considered as different because the Singapore flag, which is placed in the middle, is not rotationally symmetric. Now, the key thing to understand is that it is actually quite difficult to fit everyone in for 3 out of 8 positions to be not next to each other and not opposite each other as well. So for example, if the first student stands here, from let's say the first Chinese student stands here, this position, and this position all cannot be used. Which means that your choices are just going to be either this or by symmetry the other way. Coincidentally, the crosses that I just erased would kind of be one of the only options for how the other 3 students, let's say the Malay students, could stand if the Chinese students stand here. Because one of this pair, and well, this is forced. So first Malay student would need to stand here, and for these positions, you can only either be here or the other way, because you need to make sure that the 2 Indian students also do not stand directly opposite each other. So you can either be here or it can be the other side. So that's actually not many, and we just now need to count this without getting confused about rotations and reflections. So how I want to think about it is that, let's say for my first group of students, let's say I put the 3 Chinese students here first. Now, I realized that all the arrangements we described can be thought of as just an isosceles triangle. And since it is just that one isosceles triangle, I can just say that to place the 3 dots, these 3 positions, there are just 8 choices. Now, for any of these choices, based on what we have just said, there are only going to be 2 choices for the positions of the 3 Malay students. It's going to either be here, or alternatively, it could be here. And then of course the 2 Indian students, we have chosen it such that the 2 positions are not opposite each other or adjacent to each other, so no problem there. Now take note, at this point we have just used red dots and blue dots and red dots and black dots and whatever color it is to denote the positions they should occupy, we have not yet actually placed them. And so the actual answer would be 8 times 2 and then 3 factorial, 3 factorial, 2 factorial for the positions of the students themselves, because the students are not identical to each other. Okay, and so this would be 16 times 6 times 6 times 2. This is equal to 1152 ways. Now, as a sanity check, you should always just see that this is not too big or not too small. So the 3 factorial, 3 factorial, 2 factorial are just for rearranging them among their own designated seats. But if let's say that it is 8 factorial, which is 40320, that's a very crude upper bound. So this seems to be somewhere in the ballpark of a reasonable number. Question 6. Sign or gap. I thought I was pretty clever in coming up with this acronym, and then I realized that I have a headache in trying to simulate a gap and a sign, because these two things are not quite the same. So I've decided to use a sequence question, and the problem is that when you keep on taking sign of something, it just gets to ugly, irrational stuff that humans cannot deal with. We need a calculator for that. And so I've actually included in a slightly contrived function over here in order that we now have integer values. Okay, so this is our condition. You start off with 1, and then you have two choices. Either sine pi over 2an times n plus 1 squared. So if I took this option, the sine option, then I will get sine pi over 2 is 1, so it just gives me 2 squared, which is 4. If I took the gap option, it means I stay at 1. Now we can ask ourselves, why would we want to stay at 1? Well, that would depend on the next step. Now for the next step, we obviously can always, we always have 1 as an option. But the sign will look different each time. Now if this is 4, then sine 2 pi is 0. So this would send you to 0. If this is 1, then you're going to get, now n is 2, so you get 3 squared, which is 9, and this is a little bit better. So now you've got 0, 1, or 9, and your possible outcomes, you realize, are always going to be something like that. Meaning that this here is going to be always a square, and we know that a square is going to be 0 or 1 mod 4. Which means that you never have to worry about a negative number showing up. That's the good news. If it's 0 mod 4, then your sine of pi over 2 times, well, 0 mod 4 means a multiple of 2 pi. So this will give you 0. And if it is pi over 2, it gives you 1. So it literally just is going to be sometimes a 0, sometimes a 1. And so your three possibilities are always going to be the square times 0, the square times 1, or you reset to 1. So for example, at the next step, 0, all of these, if you take a gap step, this can always go to 1. But if you apply the sign option, 0 goes to 0. It's very silly. 1 and 9 both go to 16. Right? And if we were just to trace this out again one more time, when this is an even square, it will not be able to jump to 25. If it's going to jump to 0, if you took a sign, only 1 would allow you to jump to 25. So now I want to make this sum as big as possible. And obviously, you can realize that, okay, there is never really a good reason to go to 0. Means that if the sign is going to send me to 0, I might as well be at 1. Because 0 is not only bad now, 0 is also bad for the next step. Right? 0 always leads you to two choices, 0 or 1. So there is not any latent hidden potential in picking 0 at any point in time. We just don't ever want to use the 0 step. That's just bad. Which means that all we have is just the option of 1 or the next square. But the interesting thing we see is that the even squares cannot go to the odd squares. So you kind of have this option here, right? It's going to be that first thing is 1. And then you can either get 4 or 9. And then you can either get 16 or 25, but you can never get both. Which means that very naturally, you should just take the odd ones, right? Because the odd square is bigger than the even square if we cannot keep both. So you want to go with, let's say, stay with 1, so you get, and then 9. And then go back to 1, and then pick 25. Since we cannot pick both squares in a row, we might as well pick the bigger one. And so this is going to give you, first of all, in the even positions, they're all going to be 1. You're going to get 1, 0, 1, 1 once, and then 1 squared plus 3 squared plus 5 squared, all the way to the last one, we are going to get 2023 squared. We are keeping all the odd squares. Now I asked you for the last 2 digits of m, so this is m. And you now have a bit of a number theory task to find what are the last 2 digits of this. The good news is that these are quite well behaved. They are all just odd squares. So I can write it as just a summation. Now, I'll just put 11 at the front, since it's going to be mod 100 that I care about. And for this, I will write it as the sum from n equals to 1 to 1012 of 2n minus 1 squared. So this is 4n squared minus 4n plus 1. So little bit of work here. Your identity is n plus 1, 2n plus 1. But the good news is that it is divisible here by 25 and 4. So this actually is just going to give you a 0 mod 100. You don't have to calculate that. So that's the reason why this is not so bad computationally. So 1012, 1013 over 2. This one's okay. So 11, this is 0. 2 times 12 times 13 will give you a 12, and then this is another 12. So your final answer is going to be 35 as your last 2 digits of m. Question 7. PR agonies is, there's quite a number of you who probably have experience with this, where cost for PRs are substantially higher than that of Singapore citizens. And so I felt that this is a suitable question that we can actually ask to do with two different price levels. And this looks as if it's just a random PSLE problem, until you think a bit more and you realize that no, there's no way that I can possibly find the values. And also there is this hint with a whole number of dollars. So there is this allusion to the fact that, okay, this has something to do with number theory. But nonetheless, let's just organize the information with our sizes. So we have got the two groups, group 1 and group 2. We've got the size and the cost. And the cost of tickets for the first group of PRs is $28 more. So I'll just call it N plus 28 and N. The size, there's a difference of 8. So 8 fewer people, M minus 8 and M. And the first group paid 50% more for their ticket. So it means that M minus 8, N plus 28 is equal to 3 over 2 Mn. And this is just a Diophantine equation. Let's expand this a little bit. Eight times 28 is 224. And then I will multiply by 2 first. Don't like fractions in my Diophantine equations. And then shift everything over. Now at this juncture, we have the classic idea, which I call completing the factorization. On AOPS, it's called SSFT, right? Simon's favorite factorizing trick. Which basically is that you want to make this a factorization and you are willing to pay the price of this no longer being 0. So you do this by factorizing the front, and then if the back is going to also require factorizing, then so be it. Obviously this does not exist. The 16 times 56 was just from thin air. And so that means that M plus 16 and minus 56 is, oh no, this is very negative. Okay, so let's flip it around to make it positive, and that also gives you a bound on N. So we have discovered that N cannot be too big. What, 16 times 56 plus 448? That's 896 plus 448 is 1344. Which we should factorize, but we do know from all the calculations we have done that this is going to at least be divisible by 16. So I can straight away factorize it, divide by 16. And this would be 84, so a bit more factors of 2, it would be 2 to the power of 6 times 3 times 7. I did a video on factorization. If I can't factorize this on the spot, that will be a bit embarrassing. Now, question is the sum of all possible sizes of the first group, which is m minus 8. So never mind, we just get all possible values of m and then we minus 8 from there. So, however, it would make more sense that we just ask ourselves, what are the choices here? This is going to be just anything less than 56. And this value down here, if we divide it by 56, is going to be 24. So this is just anything more than 24. So all of your factors, the m plus 16 should be more than 24. There are a lot of factors in here. There are 7 times 2 times 2. There are 28 factors in here, and I don't really feel like adding them up. It's going to be quite big. For example, it is possible that n is 1. So n is 55, so 56 minus n is 1, and m is huge. And so those are a lot of big values. So what I'm going to do is that I'm just going to sum all the factors first. The sum of factors would be calculated in this way. I'm very familiar with powers of 2, so I kind of like this. All of these are powers of 2. $4096 minus 32, this is 4064. That's the sum of factors of this thing. Now, out of these, I have to discard away all the small ones, which are at most 24. So I just go through the list of small numbers, and a whole bunch of them are going to be excluded, but they are still small, so I don't mind. Then there's 21, and there is 24 itself. These are the small numbers. It adds up to 168. And so all the rest, your sum of m plus 16 values would be equal to this minus this, which is 3896. And down here, we have got 6, 7, 8, 9, 10, 11, 12 possibilities, which means that there are a remaining 16 possibilities down here. So since you actually want the sum of all possible values of m minus 8, so you want the sum of all possibilities of m minus 8, each possibility, the difference is 24. And so this gives you your answer, which is 3512. Now, lastly, we have question 8. As a bit of a fun fact, so when I thought of Praise Ong, the Member of Parliament for where I stay is Mr. Ong Yi Kang. So this was something I thought, and then I felt that, okay, I don't think there is anything that I can possibly write in the question about Minister Ong that is going to be politically correct and yet an interesting math problem. So I decided that random fictitious primary school with a random math teacher, Mr. Ong, is a safer question to write. And this is actually a very famous question. It's on basically square triangular numbers. And I just made sure to say the square of my cousin's age, because as we know, cousins can be very old or very young, so you don't really get a whole lot of information from that. So this is a square triangular number. That's really what we're trying to find, right? What's his score? If we write down that this is m squared, and this is just the sum from 1 to n, the question is, when can you find a solution to this? And I'm sure that if you wrote down the triangular numbers, the first few, you will find, oh, there's 36. But if you continue writing, it will take a little while. It will take a little while to actually, get to the next square number. And there actually are infinitely many. So there's a reason why I need to block on both sides that he scored more than 50, he did not also score more than 10,000, because there are very big solutions to this as well. Now, n plus 1 equals to m squared is quite interesting. Now, this is quite interesting because let's multiply it over first. Now, n times n plus 1 is 2m squared. What we normally like to do is that we like our difference of squares, right? So what I'm going to do is the classic difference of squares. I'll just take n plus half squared minus 1/4. And then now I'll multiply this by 4. Unfortunately, this is not particularly useful in the difference of square sense. I mean, if you factorize it now, you just get nothing. It was already factored to begin with. But if you were to flip this over, you get something in the form of our Pell's equation. Our Pell's equation, if we recall, is something that is in the form x squared minus dy squared equals to 1, where d is not a square. D is a square, obviously that is just a difference of squares. So this is not. This is in the form of x squared minus 8y squared equals to 1. Now, the smaller solution would be x equals to 3, y equals to 1, and that would correspond to just 1, which is not very interesting. But we are looking for the next solution. Well, the next solution would actually be m equals to 6. And if m equals to 6, you are going to find that, okay, n is equal to 7. That is going to be the 36 over there. So this is already giving us some sort of a solution, but we hope for something a little bit better. Sorry, n is 8, not 7, my bad. So how do we get the solution after that? We need to know how to solve Pell's equation. And the way to solve Pell's equation is as follows. The first thing is to find the smaller solution, which we sometimes call the fundamental solution. That is xy equals to 3, 1, as we have said earlier. Now that means that all your solutions will be generated in the following way, which is that you use 3 and 1, and you take 3 plus 1 times square root 8. And this will give you the rest of the solutions for integer n, positive integer n. Now, let's say we take n equals to 2, you're going to get 17 plus 6 root 8. So that's the thing that you're getting earlier. It means that xy is going to be equal to 17 and 6. I apologize, I shouldn't use n because you might think that it's the same n as just now. I'll just use something like r so that we are not confused. It's a totally different thing. It's just the powers of 3 plus root 8. So this gives you the first solution, but this is corresponding to n equals to 8 and m equals to 6, which is the one we found earlier. So we need to take the next one. The next one would be 99 plus 35 root 8. And if you check this, n is 49, m is equal to 35, m squared is 1225. this is your next square triangular number, which is going to be your numerical answer. Something which is at least vaguely plausible that you could do in 10 minutes. You got 1225, which means something like 2 per second. That is very fast, but still barely conceivable, right? Anything beyond this is quite ridiculous, because the next one is going to be very huge, right? If you just square 17 plus 6 root 8. Yeah, you're going to get something which is fairly huge. You get n is equal to 209, yeah, and so 288, m is 202. That is way too big for anyone to have feasibly gotten something like that. So 204. Okay, so the next one is just way too big already. So that's it. A bunch of 8 questions inspired by our National Day theme, and also not as easy as you might think. Now, many of these problems kind of lie in a very strange spot, which is that they are a bit too hard for SMO round 1 average question, but they could appear as a difficult question. If you will have all your questions of this difficulty, you'll be in a lot of trouble. But I think standalone, some problems are like that, so it is still within the realms of acceptability. Thanks for watching, and see you again next time for more interesting problems.